Good morning, everyone. We are just after 11 a.m. Eastern, 9 a.m. Mountain Time. My name is John St. Louis. I am the Director of Marketing at Sierra Wall. I'd like to thank each of you today for attending this Gas Academy event. On today's topic of natural gas sampling, we have Jim Klentzman and Fabio Arenas from Welker as our subject matter experts and presenters. Jim is a technical expert with Welker for nearly 28 years now. Has hands-on experience with sampling installations in natural gas plants, petrochemical plants, and refineries. Holds 3 U.S. patents for sampling products and has traveled extensively in Mexico and South America, designing and installing sampling systems. We also have Fabio Arenas, Territory Development Manager for Canada and Latin America, with more than 40 years of experience in the oil and gas sector, mainly in the areas of hydrocarbon flow measurement and hydrocarbon treatment. Before I hand it over to Jim, I have just a few housekeeping items. The presentation should run approximately 45 minutes. We will take questions in real time during the presentation. Please use the Q&A or chat feature found in the Zoom control panel to submit questions, and we will answer them throughout the course of the presentation. This presentation is being recorded and will be made available shortly after today's presentation. With that being said, I will now hand it over to Jim to take it away.
Hello, my name is Jim Klentzman, and as he said, been with Welker for the almost 28 years. And so I will start with this video presentation and practical considerations for gas sampling and gas sampling systems. What we start out with is the 4 fundamental questions: why, where, what, and how. And basically, you're determining quality of the gas. So that's basically the questions there. And you want to obtain a representative sample and determine the value of gas being sold. If it's that color right there, it's usually a low BTU gas. What is a representative sample? This is determined by the different organizations, the ASTM, the API, and the ISO. And you can read what is being said on the screen here. And but basically it's just designations and how to sample correctly, and repeatability. That's more important. So why do you sample? For custody gas transfer allocation, gas plant balance, product quality, because the contract says we have to. But basically usually on the gas sampling more extensively is out in the field on a custody transfer situation, and the gas is being determine what is coming from the producers and the wells, and then it's brought into gas plants to do the distillation separation and knock out the separate components. And so therefore, with the custody transfer comes the allocation and then your gas plant balance, what type of liquids are being produced, and the natural gas liquids. And so you can determine that in so many barrels per 1,000 and gallons per 1,000, and that's how they determine what's coming to the plant and what should be coming out of the plant. The sample point is location, location, location is the 4 most important issues, and the most important is having a probe in the pipeline center 1/3, because if you do not have that, then all the expensive equipment externally to that really is negated by the fact that you do not have the gas flowing down the middle stream. You would have the gas coming off the wall of the pipe. So here again, we're talking about the location. The geographical placement has everything to do with it also. Your colder regions determine a different type of gas sampling than you would in your hot or warmer regions. So that's kind of the location part of the actual geographical, not as much as the location on the pipeline, but that's also a very important part. You want to have the proper probe placement on the pipeline, and then the flow study of internal flow conditions internal to the pipelines, downstream of elbows or different disturbances would create vortexes, and it would create pressure drops, and therefore your gas will change. The quality of the gas will not be the same in an area where you start having vortexes, because the fact is you'll be doing sometimes a 2-phase, or either your richer gas would be collected there where your lighters would be on the top. So it's necessary to put your gas sample downstream 10 pipe diameters for the probe installation, and so you don't get in an area where you have disturbed Uh, elbows are very famous for making a spiral effect or barber pole effect. So therefore it spins out components. So there, it is not good to have a probe uh, located on the pipeline on or anywhere near elbows. You need to be at least 10 pipe diameters downstream. So, and also the sample points, you want to be sure you're sampling the gas for the correct pipeline. If you're downstream of headers and different things like that, you can have the different components of the gas separated out. So you would need to locate a probe on this part of this pipeline if you were wanting to sample this gas stream. So, and this is the other parts where you do not want to put your sample probes on headers. You want to have it in the flowing stream of the gas that is being sampled to be representative of what's being in the pipeline. So the extraction point it's typically on the top horizontal area of the flowing gas pipeline and downstream of your disturbances in the center 1/3. So also in those conditions, you want to have your ambient temperatures and the temperature of the gas itself where you're going into your sampling apparatuses to make sure you're outside of these regions established by these gas curves. And so therefore you make sure you're in a gas phase and not in a liquid phase or in an area where you'd have a two-phase region. And this would be determined by how rich your gas stream is, your C3s, C4s, C2s, on your 1010 BTU gas, where it's pipeline quality gas, where you're basically would be a 98% C1 and the rest C2, you wouldn't have any of these components right here. It is very easy to sample the gas. But once you get into an area where you start having the heavier components, then you got to be more precise. Make sure you're staying outside of these, the regions the phase envelope determines, and that's determined also by, they can do the calculations with the BTU value of the gas stream. So here are some of the different documents that state how to sample natural gas. GPA 2166, API 14.1 has come out with the heated gas samplers, and then your other ones are determining the type of gas sampling or what cylinder you're using or different things like that. So it's good to read these documents before you're into the gas sampling business so you know what you're actually needing to do. The three types of sampling we'll be talking about here is the spot sampling, the composite sampling, and then also the online analysis, which is a continuous collection of sample for analytical units for gas chromatographs, or they can be for your H2O, H2S, CO2, sometimes oxygen, usually rare for oxygen unless it's some other situations, but that's basically what they look for in the online analysis when you're sampling a gas stream out in the field. Simple sampling system components, your central components, like I determined before, is your probe and your pump. The probe is the most important out of all of them, and pump, your transportable containers, CP cylinders, spun cylinders or single cavity cylinders, your timer actuator controller, and then your valves and the tubing. Optionals are needed as instrument regulators, relief valves, filters, heating apparatus, or extension tube, or pigtail. If you're working with a single cavity cylinder, doing your fill and purge on startup, this is not also an option. You should have an extension tube or pigtail on your cylinder at the startup when you're doing the conditioning phase of your cylinder to start the composite sample. And also your spot sample. Methods are the fill and empty, constant pressure cylinder, and the positive pressure with the helium, and that's for taking your spot samples and your evacuated cylinder or vacuum. This right here, typically out in the field, the technicians will open the valve to see if there's a vacuum left on the cylinder, and so therefore that degrades the type of sample. But what is more typically done is the fill and empty, and unless they're needing more samples to go to the lab, and they can use the constant pressure cylinder. So here are some of the ways, methods, according to API 14.1 to take a spot sample. As you can see, the probe is in the center of the pipeline, center 1/3. is the recommended area because of the fact that if you have higher velocities, you do not really need to go to the center, especially on your larger pipelines. You're getting to 24s and different things like that. You can go 8 inches off the wall of the pipe is what they recommend. And so therefore, how you place your cylinder to take a spot sample, and here's your purge pigtail with your valve and your restrictor on the end of it. The technique you would use is opening these valves fully. You deal your fill, and then you shut the valve, and then you purge it out to almost empty, and then you do your fill and empty. And on GPA 2166, there's a determined amount of times you do that depending on the pressure in the pipeline. Lower pressure pipelines require more fill and purge. Higher pressures, typically less. 1,000 PSI usually is like a 4, average 4 fill and purge cycles to completely clear out the cylinder and get it ready. And then you can close in your valves and take it off and take it to the lab. This is not recommended where you put the cylinder in the line, but due to the fact is when you're doing your fill and purge, you have coming out of your probe, you have a velocity reduction in this cylinder before it goes out to the purge side, where this right here, any accumulation of liquids would be going out the bottom valve. What they call these typically in the field to knock out liquids and collect them at the bottom is called a separator. So therefore, you really don't want to do this type of apparatus. I have seen it done, in your 300 and 500 cc cylinder is very negative impact for that. I've seen smaller cylinders, the 75 cc, where they have actually got results out of this method, but it is not the preferred method. Your preferred method is with your cylinder pointed downward in a vertical position. Constant pressure cylinders are different. You can set them vertically or horizontally like this, but your spun cavities, single cavity cylinders need to be in the vertical pointed downward. So therefore your properties filling and emptying will allow any liquids accumulated to escape. There's also a device where you can clamp around the cylinder prior to taking your sample, and you can heat it up, plugging it into a vehicle, and you'll bring it up to 140 degrees, unplug it from the vehicle, and you can take the heated cylinder and jack it out to the line and pull your spot sample. You can also do that with composite sampling. Here are some examples of probes. This is just regular probe right here with a straight cutoff is what you would require. This shows a 45 and this shows a scoop on it, but unless you're trying to establish a flow through a pitot probe, you really, you would need a scoop on it to actually get a flow, but you don't want to take this loop way far away from the loop from the pipeline. You want to keep it in proximity because that will not create flow with the velocity in the pipeline to go through here for a long distance. Here's another example of a pitot probe, but typically for sampling of gas, you just need a probe, simple probe, straight cutoff is the best deal to do, and it'll get you the best sample in spot and in composite sampling. Here's an auto insertion style probe. If you ever have a pipeline where you cannot insert a probe to it, or there's a probe not there, there are ways to be able to insert a probe through a ball valve with this very simple apparatus that you can set the lock collar to the depth required. And by manipulating these valves, you can insert it into the pipeline and then retrieve it once you're finished taking your spot sample if desired. Here are some of the cylinders we were talking about. These are what we call the single cavity or spun cylinders. This is what they call a dual cavity or a constant pressure cylinder or 2-chamber, where there's a piston inside separating the gas or the product from the pre-charge side. So they're very good for colder situations. Here's an examples of some spot sampling manifolds. And as we said before, you can see this is the spot sampling manifold they use on GPAs. This is a drip pot where it impinges against the side and the gas comes out over the top and into your cylinder. You leave it purging where you're doing your fill and purge method, and here's your pigtail associated with that. Problem with this, if you're sampling a rich gas stream and then you go to a lean gas, you need to clean this out, either some type of steaming or acetone or some type of a solvent to clean it out in between gas samples, a non-hydrocarbon based solid, so you can clean it out. Because if you leave a rich gas deposits in there and go to your 1010 BTU gas to take a spot sample, then you can have some overriding components getting your cylinder from that former sample. Here's another way to take spot samples where you actually have a sight glass and it's used to knock out the liquids or components in there, and you can actually see what's going on in the gas as you're taking the sample. If you see a gas like this, when you open a valve, that's a richer gas, and plus it's also an EPA environmental impact that's you're not supposed to do around areas that are very restricted to allowing methane to the atmosphere. Here is an example of another type of spot sampling manifold where we use a WFS3, a model I call it, and as you can see, the gas comes in there, spins around, impinges, your liquids go out there, and then you have to turn and come back up, and then you go into the probe and back down into your cylinder. Very good way to knock out liquids associated with spot sampling in pipelines. As you can tell, when you're taking that style sample, you can see the phase being changed in there, and you can see if any liquids are accumulating in there. So it's a good way to determine if you have a good spot sample in your cylinder free of liquids. As you can see, it's just how it's set up. There's your drain and out, and the newer ones have the drain out the bottom. Not the drain out the bottom and the gas out the side and the entrance to the top. So here's an example of it again, where the gas comes in top, hits the centrifuge, and spins the gas before it has to take a turn, go back up, get into the tube, and go out to your cylinder. So therefore, it creates a disturbed path of impingement for your richer gases. It would have your condensates and liquids in the stream, your water, and you can actually see if you're actually making any type of liquids or anything that could be accumulating in your sample. Next, we also have the we also have the spot sample panels that are used in your different refineries, petrochemical placements. These are used where you flow through continually to the bypass loop, and at the time of sampling, you shut the bypass valve and opening it to your cylinder and let it flow through there. They typically let it flow through there for a certain amount of time till you know you've got all your purged out, and then you shut your cylinder valves on your cylinder, and you can blow down the line going to your quick connect from your valves in this area right there, and then you release the cylinder and take it to the laboratory. When you take spot sample, daily, monthly, semi-annual, seasonally, basically it's when the supervisor instructs you to. They typically will watch when you're taking composite samples. A lot of companies will take a monthly. They're taking monthly, most composite samples on your custody transfer. So at the end of the month, they will take a history of the BTU being recorded in that, and they'll take usually like a 6-month average. And so if you go either high or low on that type of situation, out of a 10% plus or minus range, they will flag the sample, and that's when they'll send you out to take another spot sample. Typically, that is when that is done. So, but depending on the production, typically your wells that are producing less, they will take spot samples, sometimes 6 months, semi-annual, seasonal, monthly. When a well, it's on a single well, a gas well that's producing gas, typically your monthly spot samples, if you're not taking composites, you'll take your monthly to determine what your BTU value is in your composite, not your composite, but your components in your gas stream. So that's typically what's done. On the smaller wells, they'll go semi-annually and seasonally, because the well will not change the components except over a long time period, typically as the well degrades. And we have this statement there too. Okay, going to composite sampling, it's a lower cost alternative to online analyzers. The sample collected by properly designed, installed, compatible, provide a representative accurate sample of the product. And they're all standalone units. And when they can be, they should be interlaced with a flow measurement equipment so it can be collected proportional to flow in the line. And that is usually done by pulsing the solenoid on the sampler itself by electronic flow measurement device or DCS, depending on where your location is. But typically out in the field, you'll have either a 12 or 24 volt flow computer. Sometimes they run powered by solar panels. But the gas samplers we use, they use a small solenoid, so you can run it a long time without having to worry about consuming the power of the EFM. Once again, you go to the areas where we reviewed before for the same thing. The only difference is you're no dead ends, no streams that are not flowing. And that's for spot sampling, but also you get into the heating components for your composite samplers, and that's what we'll be discussing in a little more detail. Location for your spot and your composite sampling, usually you're taking the first tap down from the orifice plate, which is your orifice plate in your gas stream, your measurement device. Downstream from there, typically there's a 3/4 inch MPT with a 6 inch differentiation from the following ports. And so you would want to install your probe on the first inlet. So you're down so many pipe diameters 10 from the orifice plate, so you'd not create any turbulence. If you see this probe looks like a pitot probe, but this probe is really just, they're using it as a single probe, and they were using the pitot side as a back pressure for the composite sampler cylinder, which would be a dual cavity cylinder. So they're having your pre-charge on the backside by the probe. So that's why that's done there. If you would put this probe here and you would have a thermal well here, then you would have a turbulence and disturbance for the probe to catch. And so therefore your components can be degraded by the disturbance in front of the probe. So you want to keep your probe clear of any disturbances. Typically, most samplers, a lot of the bigger companies now are making, doing the installations where the sample is probe mounted. So all the components are right here on the probe. So you don't have the length of tubing going into your ambient conditions. And this is just another statement with your data in line and your properly designed place of service affected by ambient conditions or fluctuations of pressure in the line. Ambient conditions are what you would be more associated with. The pressure in the line is not too bad, but your ambient conditions can really affect your gas sample. This is some of the different style composite samplers. As you can see, we have a smaller MPS2, has a 0.25 actuation per each one, and then your probe mounted GSS4s and with your constant pressure cylinders, and these can also be arranged where you have the cylinder hanging off from in front of the samplers. There's more examples of how you should locate your sampler. This is actually mounted on a LE2, which is a liquid eliminator. So if you have real rich gas streams with wet gas, which you have as water content, this has a hydrophobic membrane in there. So when you take your composite gas sample, there will be no water present, and typically all your hydrocarbons and your gas in hydrocarbon in the gas phase will make it through the membrane because it's large ported and make it to your gas sampler and then into your cylinder. Here's some other examples of probe mounted gas samplers, and this is just an example of how it would be set up in the field with your purge valve there. You have your 2 valves on the cylinder, and then your pigtail valve on the end. So you can go in there and open these 2 valves completely, and then use this valve for the fill, and then shut the valve, and then you empty the cylinder and doing your fill and purge method. And therefore, at the end of the cycle, you let it down to almost 0. And you can see by feeling the end of the valve right there that you still have a little pressure left in, and then you shut your bottom valve and shut your purge valve completely before you do that, and it'll be let down to 0, let out their gas, and then take where you purge your pigtail, and you're ready for your composite sampler for the time period being sampled. These are some of the areas where you would find the composite samplers. Everybody asks where they're located. These are the gathering areas, and there will be a composite sampler inside of this enclosure right there. And this enclosure is better regulated for the ambient environment, so it's not affected so much by there. And as far as the composite sampler, should not have filters of any type, although we just said on the real wet gas, they use membranes sometimes. And then install between this probe and the sampler. Drip pouch definitely should not be used. What I see some people want to use is large filters, and those are for instrumentation supplies, not for gas sampling or analyzer supplies. There are designed pieces of a component equipment that you can use for your composite samplers and on your online analyzers that have very small space in them, so you can purge out the area and get a good sample through them. And so, to have proven that condensate collection in a standard cylinder mishandling lab can increase the BTU gas sample by a considerable amount. One drop of like a butane or C6 plus, if it's dropped and loose in the cylinder, they can heat that up. But everybody's, well, you can heat it up and turn it into a gas. Well, when you heat things, that increases the pressure, so it keeps that in a liquid state, because you really can't get that back into a gaseous state by heating it if the pressure's high enough on the cylinder to affect that. But also, the problem with that, the single cavity cylinder is when you start letting the pressure out of it into your GC at the lab, it can actually pressure will be reducing, so you can be gasifying those condensate droplets that could be in the cylinder. So therefore, it increase your BTU the more times you let the gas out of the cylinder. So there are ways to fight that, but on most time it's better off using the constant pressure cylinder, real rich gas streams when you run into those wet situations. So talking about the heating gas samplers, the hydrocarbon dew point that was shown in the phase envelope, it shows that you want to be so much above the dew point, I believe it's 30 degrees, and stated in the APAF 14.1. Cold sampling equipment can have a detrimental effect because the fact is, just like a glass of iced tea, when you're getting the condensate outside, a cold cylinder with damp gas inside of it can condense inside the walls of the cylinder. So therefore, they recommend your heating of the cylinders or some type of conditioning before you do your fill and purge inside of that. So like I said, you want to be 30 degrees above the expected hydrocarbon dew point, which is determined by your phase envelopes we were showing earlier. So, and here it is again. So therefore, you want to stay outside of those areas. You want to be in this area right here. So make sure you don't have a two-phase gas or either going into your liquid phase. So as you can see, your pressures and your temperatures, your pressures and your temperatures are recorded there. So as you drop the pressure or the temperature, you decrease the area where you can get where you can stay in a gas phase. So therefore, for your actual analyzers and different things like that, that you're reducing the pressure from a high pressure to a lower pressure. If you stay in these areas right there, you will not get your liquids forming in the stream. So that's why you use heat trace tubing and the different things on your analyzers to keep these areas and keep them in the gas phase. Heated composite samplers, there are different ways to do that. Typically, it's with an enclosure around the composite gas sampler with a heating element. One of the things we use a lot is the catalytic heater, and Welker has a design where we use the catalytic heater and all the components are inside the enclosure. And this is typically what you would see in a heated gas sampler. We very rarely use the GSS4s because the fact is the heat keeps all the gas in the gas phase, and the vanishing chamber benefit is not as likely to benefit you in a heated gas sampling system. If you have electricity, then you can go heat it by electrical, by snap action solenoid, keep it about 120 inside there. And then you have your heated components all within there and inside that enclosure. One thing I want to note here on the catalytic heater, it's very important. A lot of the other heated gas samplers, they take their feed to their catalytic heater outside of the unit into the ambient and then return back to feed your catalytic heater. If you do that, you're looking to have some retrograde condensation occurring in the tubing outside. And when you bring it in, you'll introduce liquids to your catalytic heater. So therefore, you will basically poison it and it will stop working for you. There are other problems associated with catalytic heaters and your richer gas streams. That's one way we have addressed the situation where you have a filter and then you come down and then you have membranes in these other little regulators to keep things out. But in this catalytic heater, we supply a port on there so you can put a inches in water column gauge there so you can test your catalytic heater component, which is your thermostat, and on startup. And when you click it on and click it off, there are certain amounts of inches of water column that you should see on there. And the main problem with these is if you're running it, it's usually very good, very well. But when you cycle, it gets hot enough and that thermostat cycles off, there should be 1 inch of water column available at that time. And a lot of time there's a little orifice in here that can stop up, therefore shutting off your gas, preheated gas that's on the cycle phase of your heated catalytic heater. So there's things that can be done to keep that from happening by your filtration and also your proper adjustment of your range before you put your catalytic heater out in the field. And also the fact is we feed to the gas sampler and the gas sampler has a flowing stream through it, feeding the catalytic gas heater, going through the regulator, and then goes from there over here to feed the filter going down to your catalytic heater. So therefore, you have a continual flow of gas go through there and being burned by the catalytic heater, which is, well, it's catalyzed, don't say burnt, but what that does, it produces the CO2 and water after the methane that's been going through your catalytic heater. So therefore, there are ports associated with the top part of the enclosure and the lower part of the enclosure to let your water vapors out the top, and then also to let sufficient oxygen in to keep your catalytic heater running. And I'm kind of concentrating more on the catalytic heater style of the composite sampler due to the fact I'm talking to people in Canada. But like I said, there are ways to keep these lit and keep them running properly. And you have a diagnostic tool on there that can be able to set up. So when you're out in the field and it's not working, then you can diagnose what the issue is with it. So the other type of the component though is the good part of that is that you have a flowing gas stream continually through the body of the gas sampler. And when it actuates, it is taking along with the purge going to the solenoid through the regulator, you also have a continual feed through there too. So that makes it nice. If you ever have a malfunction of the thermostat and it overheats the enclosure, we have a secondary thermal check valve right there in that area right there. And it actually has this type of adhesive and there's a metal ball on there. And so at 250 degrees, that adhesive will turn loose and let that ball drop down. It will shut off the flow to your catalytic heater. So you don't have an issue with it being getting too hot in there. If you're ever using catalytic heaters also, we always try to keep our sampler with just the solenoid operating from an EFM by this area right here connected to it. But if you ever get out there and you see a type of gas sampler, catalytic style, and the controller has a controller timer associated with it, those batteries need to be left outside of the enclosures. Some of the other companies, when they first made these, they left the timer controller inside the area where the catalytic heater was, and there was some issues with the batteries igniting in the timer controller. So we do not typically use that and make that an option. But we can provide a timer controller if needed. So here's your electric heater, and that's just kind of self-explanatory, but you got to have electricity and 120 volt to operate these. And typically in a gas plant, you have those available, so that's not an issue. Out in the field, typically you have to go with a catalytic heater. There's another option to that too. If you have electrical heat, we have a block heater you can put on GSS4, and then we put insulation around it. And then you can install it with that type of apparatus. Here's your example of that GSS4, where it's coming up through the sample area, and then it's operated and comes into your cylinder. Is there any questions so far?
No, Jim, I'm not seeing any so far.
Okay, great. Well, I was taking a little question break there because I'm gonna take me a drink of water real quick. So after we get through with that, the composite, now we'll be talking about the online analyzer, as it's typically with a regulated probe in the pipeline of some sort. We have several different models. We have auto insertion on smaller pipelines where you have like a 4 to 6 inch, and you have the ability, like an orifice plates there, you have shut off valves on either side where you can actually shut in the system and blow down the system to get to your probe regulator. We have a style that you can mount right there in those areas. If you get into the larger pipelines, I would recommend doing the auto insertion style. But after you get your point of regulation, we have the regulator that regulation occurs down at the point of the stream. So you have thermal fins to counteract the Joule Thompson effect. Come in here, come to your liquid eliminators, and then your analyzer liquid shut off, and then go into your flow indicator, determining the amount of slipstream you'd want to come by your analyzer, and then you feed your analyzer. So they need to be GCs need regulated product for use, and they have the recommended use of probe regulators. Regulates in the flowing gas stream, and has the vital components of the sampling and the probe and the regulation. Here are some examples of probe regulators that are regulated, heated, and then this is just a flange version of what we call our probe regulator IRA. And this is auto insertion. You can insert it into the pipe and extract it through a ball valve. And these are recommended on where you have a larger style pipeline that you cannot actually blow it down and evacuate the pressure to be able to maintain something like you would on a smaller type probe regulators. There's not much maintenance done on these, but from time to time, there's a poppet and a seat down here in the base where your regulation point occurs. And so you have a Joule JT effect there. And so that JT effect, you're counteracted by these thermal fins from the gas or the fluid flowing over these thermal fins. So your negative, your 7 degrees Fahrenheit drop over 100 PSI pressure drop would actually can freeze up regulators when they're external to the pipeline. But on this style regulator, we have that it's counteracted by these thermal fins. So there's no way for this to freeze up, have ice ball, and have it to stop your diaphragm and all your components from working. So that's the benefit of having this style regulator, and goes out the valve to your analyzer. But the other benefit to this is the pressure is dropped right there. So you don't have to worry about having a probe full of 900 PSI gas going all the way to a regulator on your analyzer. And so therefore your lead time or your real time getting to your analyzers much less with this style probe regulator, because the fact that your pressure drop is dropped in the pipeline. So you're only taking 20 PSI or 16 PSI, depending on what type of analyzer you're running through this to your analyzer. So therefore you're in a real-time situation, which is very, when you're doing like custody transfer out in the field and it's going to a flow computer, is not as critical. But if you're controlling, like say, an hydrogen sulfide analyzer, and that hydrogen sulfide analyzer is actually running a style of pump that increases by 4 to 20 milliamp, then you need to have a real time going to that analyzer because you're controlling a situation with your controller. So therefore you need that real time. So the gas going down the pipeline will be representative of what's going by either the chemical treatment or some other type of device that is being regulated and controlled by your analyzer. Here are some more examples of your probe regulators and your direct mounted IRD regulator. And this was developed by Welker many years ago with the help of people in the field, precursors to Kinder Morgan. But as you can see, this is directed through a valve. And when you open the valve, it puts pressure onto this pot on the top. And then when you open this valve, this pressure generated by the pressure pushing on top from the gas pushes the hydraulic up and out into a piston that's located in this area, which drives this shaft on into your pipeline. And it is stopped by your lock collar right there at that point. That's why you measure before you install it, the length of travel you need to get to the point in the pipeline as determined by over here. So therefore, you would have your valve area that has to run through your riser and your ID, your pipe. And that's how you would set your lock collar to stop from inserting. This in effect also has a liquid eliminator associated with it out in the field. And so this is what we use for analyzers and GCs out in the field.
Hey, Jim, we've got one question here.
Okay.
Are the regulator probes heated to counter temperature drop?
We do have heated regulators, but you don't have to do that a lot of times out in the field because the point right there is, the JT is affected by the thermal pins. And then when you bring it out of the pipeline, usually you go into a heat traced tubing anyway. So between that counter effect and that, like up in y'all's area, what typically a lot of people do is they will take the end of the heat traced element tubing and they will leave some of that heat trace tubing so they can wrap the probe regulator, and then we supply them a blanket, insulation blanket to put around that also. So that's one of the ways you can handle that. But typically your heating for your gas chromatographs and those type of issues is not an issue for your JT being affected by it. Now, these are also used in liquids, like liquid, gasifying liquids. So in those types of situations, you would have a heated regulator. You have a heating components in the regulator. So, but typically on the IRDs, you don't have to worry about that. The heat trace tubing can take care of that situation. And along with that, we have direct mounted liquid eliminators that can actually return your liquids to the pipeline before it goes into your system that you're going to. Your analyzers, and then also we have the analyzer liquid shutoff. We have a newer style component we have out that actually has a inlet and an outlet that you do not have to disassemble the tubing or take out many of the Allen screws to do your maintenance on the membrane. This can be taken with and there's a deflector seal in there. All you got to do is depressurize it, open your top, pop out the replaceable cartridge membrane, put your new one in and put the top back on and keep on going. This is an example of that and how it comes in and swirls around and then deflects and then has to come back around and before it goes into your membrane and out. These can also be retrofitted in your Charlie horses and your LE2 to create more of a disturbance to your path so your gas is not impinging directly on your membrane, and also that gas has to come around there. So any type of liquids or fluids that would be present would tend to go out and out the drain and not get on your membrane. Here's a sampling conditioning heater system we have, and sampling conditioning heated system is what we typically call it. I nicknamed it the Charlie horse because the guy that helped me develop it was named Charlie, but it's a different kind of components associated in an enclosure, so it makes for a good installation, and you have all the previous components integral to this system. You have the enclosure that you can pull a pin to take it off the pipeline. It's good for installation and for doing your maintenance on the, but it has two valves right there, your valve on the right and the left side. And then you can shut those valves in to depressurize the system to take it apart, do your maintenance on it. Also, there's a analyzer liquid shutoff. We like to shut this valve in before we take off the heat trace tubing. And so therefore you don't have any incursion of air or anything into the heat trace tubing going to your GC. And here's the different poppet that is associated with it, 11/16 wrench. We'll take that out so you can do your maintenance on that part. Typically, we take the top off, take out your bolts, and then you can unstack the components. As you can see, here's the heater part of it. Comes in. The gas is not in contact with heating element. That is inserted to a stainless steel tube internal to that's rated to the pressure. And then we have a hard anodized aluminum component that straddles the heating element. So therefore the gas has a disturbed pathway before it makes it to the regulator. And so therefore you have a good contact and good heating exchange due to the heating element, the way it's designed. Along with that, you have your membrane down at the bottom with the screen on top. And that's what I was talking about when you have that deflector. You can put that underneath of these also, then your O-ring. When you take those components apart, typically they're on a flex tubing component. You just slide the top of the assembly over to get your membrane, replace it, and put it back together. I always like to take those bleed valves that are shut off when you do that. When you take that membrane out, take your white rag, put on top, blow it down, and then put it back in service. There's also these type of devices we have, the manifolds that you can bring in a single gas stream at 100 PSI or 200 PSI out of your sampler conditioning heated system. And then you can go to your individual analyzers. Example would be, your H2O, H2S, typically take a 10 PSI milliliter per minute flow stream. And then you have your different other analyzers to take your 23 PSI to GCs, or ABB takes a 16 PSI at a very low flow rate. And so you can heat that. It's heated and inside enclosure, and that's also available through us. It's kind of a closest above. We've got a new design in where we're putting a inlet. The inlet comes in and it'll go to the top, and there's valves in between the regulators. So you can actually shut the valves in and then have the stream come in the top or the bottom. And so you don't have to shut in any of the analyzers. You can do your maintenance on your regulator, which is only a poppet, 11/16 poppet. You can get in there and change it out and put it back in service. Any questions? I run 4 minutes over.
No, that's great, Jim. I don't see any additional questions. We'll give folks just a couple minutes in case there are any last minute questions. If not, that'll be a wrap for today's presentation.
Well, for the people at Welker, they're probably saying, who's the guy talking? He doesn't have his cap on. So, well, good.
Perfect.
John?
That looks it. Yep. Thank you very much, Jim.
Wraps it
Thank everyone again today for attending. Is that Mike on the line?
There's a question in.
Oh.
Jim, is there a difference, pros or cons for time-based collection or flow-based?
Flow-based is the way to go.
So basically pros and cons of time-based versus flow-based sampling.
Yes, on composite sampling is what you're referring to. Yes, there is very good, because like it states, when you do a flow-based, you're taking a snapshot of that amount of gas. And now when it's going like down a gas stream that's a pipeline quality gas, there's no issues with that as much as, but you still need to take a proportion of flow because of the fact that you're taking a little bite out of that proportion of the gas going by. Plus, on a time basis, if you stop flowing, you need to stop the composite sampler from operating, and then on a flow base, it stops all the way. But most of the big companies, they do it proportion to flow because of the fact it's so much better to be able to get a more accurate composition of your gas stream, especially when you're going to a gas plant and you're monitoring the liquids that you're going to be able to knock out in there and go to that way. But one other thing I wanted to talk about was, I know y'all are talking about the hydrogen in Canada, and we have plenty of components that are used with the hydrogen mixture that would be used. We have sampled that before, and the fact is you've got to watch your connections, your quick connections, and also your pressures, your higher pressures hydrogens. That hydrogen can go through different seal elastomers, and I've seen that happen personally and dealt with that here in the refineries. So that's something you got to keep in mind when you start beginning to deal with the hydrogen that you're probably going to see in the near future. So did that, Mike?
Yeah, I want to just make sure that that question was answered, the comparison of time-based versus flow-weighted sampling.
Yes.
Was that clear? I'm just asking our guests.
Yeah, it's definitely flow-based. It's much better for composite sampling.
Yeah, gotcha.
But
yeah,
a lot of times when you have wells that are flowing though, and your actual flow varies so much that you can't really set up your flow based time, to be able to get a pressurized cylinder at the end of the sampling time. And that prototype, if there's not going to be a stop in the flow, there's a way to shut that timer in. So a time based in that type of situation would be way to go, but also you can also go to a constant pressure cylinder on those applications, on those produced streams that have a lot of variation in flow. So it doesn't matter how much sample you got. If you've got 10 or 20% or 80%, you're still representative of what's coming down that pipeline, because it's, the pressure is going to be the same.
Good. Thanks, Jim.
Okay. All right. You're welcome, Mike.
That looks like all the questions. Give it 10 more seconds here. Otherwise, Jim, Fabio, thank you very much for today's presentation. Again, to all attendees, this presentation was recorded and will be made available to yourselves shortly. Keep a lookout for an email for that. Thank you again, and have yourselves a great rest of your day.